Hey guys, welcome back to HVAC Official Channel. Today we are covering the most fundamental topic in all of HVAC, the vapor compression cycle. Guys, this is the working principle behind every AC, every refrigerator, every chiller, every heat pump in the world. If you truly understand this cycle, you will understand every HVAC system on the planet. Today I will explain it in complete detail with 100% correct information. Let's go. What is the vapor compression cycle? Guys, let me start with the most important definition. The vapor compression cycle is a closed refrigeration cycle that uses a refrigerant to absorb heat at low pressure, compresses the vapor to a higher pressure, rejects heat in a condenser, and passes through a throttling device before returning to the evaporator. In simple words, guys, the vapor compression cycle moves heat from a cold region to a warmer region by adding compressor work to a circulating refrigerant. Remember, an AC does not create cold air. It moves heat from inside your room to the outside. And the vapor compression cycle is exactly how it does this. It is the working principle behind most air conditioners, refrigerators, heat pumps, cold rooms, and chillers. The cycle is nearly 200 years old, but it does not seem ready to leave the scene anytime soon. It is still the most reliable and efficient cooling method in the world. The four main components. The vapor compression cycle uses four main components. Every technician must know these perfectly. Component 1. Compressor. The compressor is the heart of the entire system. It is a mechanical device used to increase the pressure of refrigerant vapor by decreasing its volume. The compressor receives low-pressure refrigerant vapor from the evaporator and compresses it to high-pressure, high-temperature superheated vapor. This compression requires work input, electrical energy. Types of compressors used in vapor compression systems: reciprocating, rotary, scroll, screw, centrifugal. Each type works differently, but all do the same job. Compress the refrigerant from low pressure to high pressure. Component 2. Condenser. The condenser is a heat exchanger. It receives the hot high-pressure superheated vapor from the compressor. Here, heat is rejected from the refrigerant to the surroundings. As the refrigerant releases heat, it cools down and condenses, changing from hot vapor to high-pressure liquid. In air-cooled systems, air removes the heat. In water-cooled systems, water removes the heat. Component 3. Expansion valve. The expansion valve is also called throttle valve or metering device. It receives high-pressure liquid refrigerant from the condenser. When the refrigerant passes through the tiny opening of the expansion valve, pressure drops suddenly and dramatically. This pressure drop causes temperature to drop too. The refrigerant transforms from high-pressure warm liquid to low-pressure very cold liquid and vapor mixture. This process is called throttling or isenthalpic expansion. Types of expansion devices: capillary tube, thermostatic expansion valve TXV, electronic expansion valve EEV. Component 4. Evaporator. The evaporator is where useful cooling actually happens. Cold, low-pressure refrigerant enters the evaporator coil. The refrigerant absorbs heat from the surrounding space, whether it is room air, water, or a product being cooled. As it absorbs heat, the refrigerant evaporates, changing from liquid to low-pressure vapor. This heat absorption cools the room or space. The cycle then repeats. Refrigerant returns to compressor. The 4 stages of the cycle, step by step. Now guys, let me explain the complete cycle step by step. Vapor compression refrigeration systems work through a 4-stage cycle. Stage 1. Compression. Refrigerant enters the compressor as low-pressure vapor. It is in gaseous state at this point. The compressor compresses the refrigerant, raising its pressure and temperature significantly. It leaves the compressor as high-pressure, high-temperature superheated vapor. Temperature at compressor outlet can reach 60 to 80 degrees Celsius or higher. This stage requires electrical energy input. The compressor is the only component that requires power. All other components are passive. Stage 2. Condensation. The hot superheated vapor enters the condenser. The condenser rejects heat to the surroundings. In an air-cooled condenser, a fan blows air over the coil. In a water-cooled condenser, water flows through the tubes. As heat is removed, the refrigerant goes through 3 phases. First, the superheated vapor cools down to saturation temperature. Then, the saturated vapor condenses into saturated liquid. Finally, the liquid subcools below condensing temperature. Subcooling is very important, guys. It ensures only liquid enters the expansion valve, no vapor bubbles. Would reduce system efficiency. At the end of condensation, refrigerant is high-pressure, subcooled liquid. Stage 3. Expansion. The high-pressure liquid refrigerant enters the expansion valve. The expansion valve reduces the pressure of the liquid, causing it to expand rapidly. This sudden pressure drop causes flash evaporation. Some refrigerant instantly turns to vapor. Temperature drops dramatically. The refrigerant exits the expansion valve as a low-pressure, low-temperature mixture of liquid and vapor. This is called a two-phase mixture or wet vapor. The temperature at this point is very cold, can be -10 to -20 degrees Celsius or lower. Stage 4. Evaporation. The cold, low-pressure two-phase mixture enters the evaporator. Here the refrigerant absorbs heat from the surroundings. In an air conditioning system, warm room air passes over the evaporator coil. Heat transfers from the warm air to the cold refrigerant. The refrigerant fully evaporates, changing from liquid to vapor. The air loses its heat, becomes cool, blown back into the room. At the end of evaporation, refrigerant is low-pressure saturated vapor, or slightly superheated. Superheating at evaporator exit is important. It ensures no liquid refrigerant enters the compressor. Liquid entering the compressor causes serious damage, called liquid slugging. Then the cycle repeats. Refrigerant goes back to the compressor. Key terms every HVAC technician must know. Guys, these terms are asked in every HVAC interview. Superheat. Superheat is the temperature of refrigerant vapor above its saturation temperature at a given pressure, measured at the evaporator outlet. Normal superheat for most systems, 5 to 15 degrees Fahrenheit. Low superheat, liquid may be entering compressor. Dangerous. High superheat, system is starved of refrigerant. Subcooling. Subcooling is the temperature of liquid refrigerant below its condensing temperature at a given pressure, measured at condenser outlet. Normal subcooling, 10 to 15 degrees Fahrenheit. Proper subcooling ensures only liquid enters expansion valve. Low subcooling, flash gas and liquid line, reduces efficiency. Saturation temperature. Saturation temperature is the temperature at which refrigerant changes phase, from liquid to vapor or vapor to liquid. At any given pressure, refrigerant has a specific saturation temperature. This is read from refrigerant pressure temperature charts. Every technician must be able to use PT charts. COP, coefficient of performance. COP measures the efficiency of the vapor compression cycle. COP equals cooling output divided by work input. A real refrigeration cycle always performs worse than the ideal because of irreversibility, heat transfer limits, throttling losses, and pressure drops. Higher COP means more efficient system. Ideal versus real vapor compression cycle. Guys, this is important for advanced technicians. The ideal vapor compression cycle assumes perfect conditions. No pressure drops, no heat losses, no friction. But in real systems, several things reduce efficiency. Real compressors are not 100% efficient. Some energy is lost as heat. Pressure drops occur in pipes and heat exchangers. Heat transfer between refrigerant and surroundings is not perfect. Throttling an expansion valve is irreversible, causes some energy loss. A real refrigeration cycle always performs worse than the ideal diagram because of irreversibility, heat transfer limits, throttling losses, and pressure drops. This is why regular maintenance is so important, guys. Dirty coils, wrong refrigerant charge, leaky pipes all make the real cycle even less efficient than it should be. Where is vapor compression cycle used? Guys, this cycle is everywhere around us. Home AC systems, split AC, window AC. Domestic refrigerators and freezers. Commercial refrigeration, supermarket display cases, cold rooms. Industrial chillers, water-cooled and air-cooled. Heat pumps for both heating and cooling. Data center cooling systems, food and beverage processing plants. Pharmaceutical cold storage. Natural gas plants, petroleum refineries, petrochemical plants, and most food and beverage processes utilize vapor compression refrigeration systems. Practical tips. How to apply this knowledge. Guys, understanding the cycle helps you diagnose problems. High discharge pressure, problem at condenser or overcharge. Low suction pressure, low refrigerant or restricted evaporator. Low superheat, too much refrigerant flooding evaporator. High superheat, refrigerant starved, check charge and expansion valve. Low subcooling, check refrigerant charge, check condenser. High subcooling, possible overcharge. Every single AC problem comes back to this cycle, guys. Master this and you can diagnose any system. That was the complete detailed guide to the vapor compression cycle. Let me quickly summarize. 4 components: compressor, condenser, expansion valve, evaporator. 4 stages: compression, condensation, expansion, evaporation. Key terms: superheat, subcooling, saturation temperature, COP. Real cycle is always less efficient than ideal. Regular maintenance keeps it as efficient as possible. This cycle is behind every AC, fridge, chiller, and heat pump. Master this cycle and you master all of HVAC. If this video helped you, please like and share. Share with every HVAC student and technician.